This is probably going to be a replacement lecture. I think I screwed up the first lecture for section 1. Anyway, section 2. Today's the first day of official clicking for your 25 out of 25 points, hopefully, on your semester grade. Prior to this, we did 1 bonus point for every day that you were registered early. And many of you got a bunch of those. And they're all posted. Okay. Today, you don't get bonus points, but you do start getting clicks in for your participation, which will eventually transform into hopefully 25 points out of 25 on your semester grade. Before we get down to business, let me reinforce to you the SI schedule. Here it is. You can jot it down if you like. And I'll try to have this up in every lecture on the very first slide. Monday, 11:30 and then 2:30. Monday in HPA 1, room 117. And then Monday at 2:30, NSC 103. What's NSC?
Nicholson School of Communications.
Oh, School of Communications. All right, Nicholson 103. And then Thursday, Engineering 1, 383. Friday at 11:30 in Visual Arts Building. You guys, I'm not going to apologize, but I am going to express my regret that there's no SI on either Tuesday or Wednesday, at least one of those 2 days. So everything. So in other words, today is Tuesday, right? So you're going to have to wait until Thursday to review in SI the stuff that we talk about today. It's just the breaks. You know, hopefully next semester they'll have a little bit better of a schedule. All right. Also, we have a midterm exam, number 1, Danielle, coming up on Tuesday, next week. And we're going to try to get you guys ready. We got a ginormous homework tonight. Homework 5, it's already set up. The section 1 kids are already working on it. Yours will activate at 1:20 today, at the end of class. All right, it's a big one. So you want to get a good start on it. Don't wait until Thursday morning at 9 o'clock and try, because you're going to be working your you-know-what off for homework 5. It's a lot of it. Let's double check the brain burners. The last 2 items in homework number 4. And I noticed that there were some discussion threads going, and I love to see that. I know several students started threads, and I asked a few students that sent me messages and web courses, why don't you start a thread? And then I'll talk to you in that thread. And the reason that that's good, and I encourage that, is that if you get stuck on something, chances are there's going to be somebody else with the exact same question or pretty close to the exact same question. And I noticed that in the threads, the discussion threads, there's a couple people the only thing they contributed was, yeah, I'm stuck too. There's a bunch of, in other words, ditto marks. There's a bunch of dittos, which is all right. It's normal. And that's why Caroline and Darian and I keep an eye on discussions, because we want you to use it as kind of a virtual study group, a virtual study partner. And even if you can't go to SI, you can participate in discussions in web courses and get some tips and stuff like that. And a couple students posted some pretty nice tips, really detailed discussion of how to handle the brain burners. Now, the brain burners started with basically the dimensions of the first half of the motion of the baseball traveling to the outfield. And just for round numbers, I chose 36 and 42. 36 meters across, 42 meters up. Yeah, that's. I mean, you can. That's a good high fly ball to the outfield. It's not going to be a home run, probably, unless you're in a really small park. But apogee point A is therefore exactly halfway through the arc, 36 meters over from home plate, or out from home plate, and 42 meters up in the sky. That's way up there. The brain burner was pretty deluxe. You were to calculate a velocity in one of them at some later time. And then in the second brain burner, you were to calculate a y coordinate at a later time. And so to get those equations of motion and then plug in the times, you have to start with the drop time. And so that's for our strategy, that's our first move. Get the drop time from the drop distance. So when I tell you the dimensions of the trajectory, basically this yellow rectangle with red borders, 42 meters tall, 36 meters wide. Yeah, you can get everything from that. Everything you need for the equations of motion. All right, so what we're going to do is work through the strategy, and we're going to get VIY, the initial y component of the velocity. All right, and we're going to do it with clicking. So get your clickers out. Now, if you haven't used the clicker, go ahead and start that question. If you've not used your clicker before, I suppose there's a few of you. And it says no base. Now, what that means is you're not matched up to my receiver up here. So what you do is you hold the power button down until the rectangle in the upper left, the square flashes, and then you type in BB. And then you'll get a message that says go nitro, and then ready. And when you get that, that means that you're talking to my device up here. Okay, now, to get the drop time from the drop distance, you have to use the drop distance formula. Okay? So, which version of the drop distance equation would you use? A, B, C, or D? I want another monster.
You want to go get
But I
another one?
I can't risk getting another one of these Javas. These things I do not like. They're unacceptable. Either the green ones or the white ones.
I can get you a green one. It's probably safe.
No, I only have a $5 bill.
Oh,
Those machines don't take fives, I noticed. Bunch of bandits. Tell you, it's always something.
yeah.
Okay, 30 seconds. Did I tell you what the answer is? Okay, you figured it out.
Yeah, I got
Okay. 15 seconds. Good, you guys are voting. 104. Wow. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Click. All right, 110. I was just giving people the last chance. Desktop, please. We got some explaining to do. The correct answer was D. Most of you chose that, but a good fraction of you chose B. Okay, let's go back to the laptop. Here's the answer. Go ahead and make sure you write that down because you're going to need to use that to calculate T in a second. All right? But now, those of you that voted for B, there's something about B that's good and something that It's, like that old kind of joke, I got some good news and some bad news. Okay, the good news is the distance here, 42 meters for option B, that's the correct distance. That's the drop distance. These other two, 36 and 36, no way, Jose. Not for this problem anyways. All right? So those aren't drop distances, so you can cancel those ones out immediately. But I did catch a few of you on B here. Now, there's a couple problems with this, but what's the automatic problem with B? 42 is good, but there's something dead wrong. Okay? It's not t squared. A drop distance formula, 1/2 gt squared, it's got to have a t squared in it. This is just t to the first power. Right? So right there, you should say to yourself, no, Dr. B, no. I'm not going to fall for your tricks. All right? And then that leaves option D. Now, I want you to hit the refresh key. Make sure you have this equation down. And you're going to calculate the drop time. You're going to calculate drop time. Now, hold on. One question. Question was, why isn't gravity negative? Why aren't we using negative 4.9? The reason is this is a simple drop distance, and we already know the drop distance. So you don't really need to. Know. We're not trying to get a y coordinate or a velocity component. All right. So we don't need the minus sign. Yeah. So this is a 9 at 1/2 g in this case. All right, so hit the refresh key and then calculate. And when you do this, I think it's going to start with the number 1. And then you select the numbers up and down. And, I did it again. Calculate the drop time to the nearest 0.1 seconds. And it should say type in the numeric part of your answer to the nearest 0.1 seconds instead of 0.1 meters. So if your answer is 82.48 seconds, then type in 82.5. And hey, you guys, hit the send key when you've got your final answer in there. Something point something. Give me 1 decimal point and then hit the send key. All right, now I'll give you some time to figure that out. And by the way, students, you may not use your calculators, you may not use your cell phones on exam 1 or any other exam. So you have to bring a regular calculator or do without. Now, if you have a regular calculator, bring it. And start bringing it to class because as you can see right now, we're using it. And we're going to use it pretty much every day for at least 1 or 2 calculations. Sometimes tricky, sometimes cinchy. This one you need to use your square root key. All right. And I can see you guys typing in some answers. Make sure you round carefully, all right? Don't round off to the nearest second. Round off to the nearest 0.1 second. So I want something point something. 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, or 0.0. If it works out to that. 45 seconds. Whoa.
Wow.
What was that? I don't like how this displays these numeric answers. Why does it keep doing that?
Because more answers are coming in, so like
The top 5
yeah.
most frequent answers. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, a couple of you missed it. And a couple of you missed clicking in. And you know what? That's official now. You've missed one. You didn't answer. All right? So now you might not get 25 out of 25 at the end of the semester. All right? So make sure you always type in an answer, I'll always give you a warning. I'll always do a countdown of some kind, right? So do not be caught napping. Raise your hand if you answered 2.9. Sweet. All right. Now that's your first step in your strategy. Use the answer 2.9. That's your drop time. Basically, how long does it take to go from apogee point A all the way back down? And then that's the same as the amount of time it takes to get up to that height. Now, what is that good for? Absolutely, it's good for VIY. All right? Because in 2.9 seconds, you lose all of VIY. You start with, a certain number of meters per second upward, and by the time you get to apogee, 2.9 seconds later, your VAY is equal to 0. And here it is, item B, 3B. VAY is 0. That's the definition of the turning point in the motion. You stop rising at that instant of time, approximately 2.928 seconds in, and then you start dipping back down to the outfield. All right? And hey, you guys, I'm going to actually use 2.928 seconds for my calculations. Go ahead and jot that down if you want to use the same thing. You'll be a little bit more accurate. And so my next clicker question for you, hit the refresh key. This is multiple choice. Go ahead, start it. Okay. How much upward speed is lost in that 2.9? And I'm actually using 2.928 seconds. All right, go ahead and, is that me? Nope. 45 seconds. Thirty seconds. This is mystifying. 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Good. 111 people participated. That's what I want. Good. Display. Controversy time. We got a little bit of splaining to do here. We got a spread of answers. That means there's a little bit of confusion. Let's take a look at the specs here. Go ahead back to the laptop, please. Thank you. Answer is 28.69. And basically, here's how you get it. I mean, it's just G times T. So the acceleration due to gravity takes away 28.69. That should be meters per second, not seconds. This should be meters per second here. Wow. Typo. Anyways, it takes away 28.69 meters per second of upward speed. On the way down, if you're starting from apogee, how much does it gain? 28.69 downward meters per second. All right? But this is upward motion, so this is how many meters. And students, this is a question about a speed. A speed doesn't have a direction. And again, Kane, this is a case where because you're not really concentrating on a direction, you're asking about a speed, you don't need to use the minus sign. But if you do want to use the minus sign, here's how you do it. You use the delta V version. And if I've lost something, that means my delta is negatory. If delta anything is negative, that means I've lost some. All right? If I start out with 28.69 and lose it all by the time I get up to apogee up here, then that means my delta V is negative 28.69. All right? The definition of delta V here, now on the second line down, I've got it split out into individual V's. Delta V is always later minus earlier. Right? So now in this case, later is the apogee. Earlier is the home plate. Right? So the y component at apogee is VAY. The y component of the velocity initially is VIY. So it's VAY minus VIY. Question, Abigail.
I don't understand like why you made it negative and what making it negative would change, like if that would change the verbiage of the question.
It's the negative here is going to indicate a direction. Over here, we didn't really care about the direction that much. And my actual question is about a speed. So this first blurb over here in the middle, V equals GT, that is perfectly sufficient to answer this question, option B. But if you care about VIY, which we do, then you want to get a negative or a positive depending on whether it's moving upward or downward. VIY is positive, right? And it comes out of this second version, okay? VAY here, V subscript AY, that's the y component of the velocity at apogee. Zip, zap, 0. All right, goose egg time. All right, so that's just a good old 0 right here, 0.0 meters per second. That's the definition of the turning point. Okay. And then VIY, that's what I don't know what this one is yet, but I know that this one is. I've lost. And again, Abigail, I see your questions. I'll get to you in a second. Again, Abigail, this minus sign here is based on the fact that I started with positive and I lost all of it. So that means my delta is negative. Okay. Question here. Yes.
Wouldn't it also be impossible to use a negative in the first equation because you wouldn't get a negative?
Yeah, that's right. And that's another reason to use that. You know, if you use a minus sign up here, the question was, isn't that another reason it should get a negative time here? And the answer, or a negative V, and the answer is yes, you wouldn't want to use that. And what's your name again? Bria? Okay. I can't remember your name. Nicole. Nicole, question.
What I was just going to ask is that because it says upward, that's why we use the positive 9.8.
No, that's not. Anytime I ask about a speed, speed is the one that says don't bother with the negative sign. Okay, it's just like the word distance. A distance doesn't have a direction. If I say that I'm 1 mile distant from this classroom, I could be out there on university somewhere, basically southwest, or I could be somewhere up on Lockwood, up by Haggerty High School, north, basically north of here, or somewhere east on the other side of campus, a mile from here, all a mile distant. Okay, so the word distance does not denote a direction, does not require direction. And so 1/2 GT squared with a positive 9.8 is perfectly kosher, right? And sometimes that's all you need, because if you're starting at the top of the library, you drop something, you know where it's going to end up. It's going to, so if you just want to know how tall the building is, it's fine. But if you want the y coordinate or the velocity component, then you have to use minus signs where appropriate. Another question. Okay, let's keep going. Anyways, basically in this last line of the second equation blurb, the second block of equations, so forget about this one. This is the one that we erased last time. And you have a minus VIY equals negative 28.69. And so for your equation of motions, that's the component that you need in 2 of your 4 equations of motion. Right? So 28.69, and it's positive, and that means upward, because it's a hit. It's leaving home plate. It's going up in the air, traveling to the outfield. So now part 4 of our strategy outline. Yeah, you could put together the equations of motion now. And sorry, I forgot to put a subscript for y. 4a should be v subscript y of t. The y component of the velocity as a function of time. Yeah, we can do that now. Now that we have VIY, we got it. And then y of t, or y subscript f. Yeah, we can get that now. Now that we have VIY, we can nail them all down. All right. Now, we haven't figured out VIX, but we can do that in a similar manner. And then we can get the other 2 equations of motion. Very simple. The 2 tricky ones are the y component, or the y equations of motion. So let's do another clicker question. All right? Which one of these is a good equation of motion for Vy of t? Good one. "30 seconds. Read very carefully. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Good. All right. Most of you guys got it, 8%. Here it is. So the interpretation here is the y component of the velocity is whatever you started with, 28.69 meters per second, upward, plus whatever the acceleration does to it. In this case, it's taking away on the first half of the motion, right, till you get up to the top. All right, so, and by the way, this equation, once you got it, it's good for the second half of the motion as well, on the way down. Because then, after the halfway point, this negative term here will be bigger than 28.69, and you'll have a negative number. That means Vy is downward, which is, it better be on the way back down. Okay, next question. Coordinate, the y coordinate equation, y of t. Which one of these? Ooh, I see and hear people paging backwards in their notes. Very good. That means you're thinking. The y equation. And hey, you guys, on Thursday, I'm going to give you a big homework assignment. It'll be a regular homework assignment based on Thursday lecture, and it'll be a combo homework assignment for a little bit of review to get you ready for the midterm on on Tuesday, a week from today, midterm 1. Be here, but do not come in until the last student from section 1 is finished. Okay? And then you can troop in. Okay, 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Ching. Yeah, you guys did good. This is the equation. And so in this equation A, option A, the first part, distance rectangle. Initial speed times time. That's a rectangle. And then negative 4.9 meters per second squared. And notice, those of you guys that were asking, this is a y-coordinate equation. So I have my minus sign in there. And this is actually a distance triangle formula. Okay? So this is a combo. All right? Now, with this equation and the rather simple x of t equation, which is a distance rectangle with the horizontal speed, you can figure out the full ballistic arc. And you can do it on a spreadsheet, which is how I did it for this graphic in the homework. And I messed around with, the x and the y coordinates and stuff. And actually, yeah, that looks about right. But anyways, if you guys are spreadsheet maniacs, you can definitely do those equations in a spreadsheet, which is how I did it. Question?
So if it's a y coordinate, it's a negative?
In free fall, yes. It's going to have a negative 9.8, and then of course it's a 1/2 g, so it's negative 4.9. Okay. So yeah, this is a 1/2 gt squared up there, where the cursor is. Okay. And that's because when you're tracking y, it could be positive or negative. Now for this baseball, everything's positive. But if you were playing baseball on the edge of a cliff and you hit a home run far enough out of the stadium and past the edge of the cliff, it would just keep going down below the level of the playing field, down to the bottom of the cliff, and then you'd have some y coordinates that are negative. So, most people don't play baseball on the edge of a cliff. So anyways, on this one, that's that. Another question. Okay. Now, I want to do some skateboard demonstrations with you. Please, who has a skateboard today with them? Raise your hand. One. Please come up. Who else has a skateboard with them? Only one?
There's one back there, someone's lying.
If you have a skateboard, please bring it up. We need a skateboarder. We need 2 skateboarders. Whose skateboard is that in the back? Don't be scared. Come on, be brave. You're going to get a round of applause when we're done. Is that your skateboard in the back? No? So nobody's... Yeah, see, I can see you back there with the baseball hat. You're behind that girl, and you don't want... Yeah. Is that yours? Come on down. I mean, you don't have to, but if you want to, you can. It'll help us. He had his earplugs in. Yeah, it'll really help us. This is going to be good. All right. Lights all the way up.
Yep.
All right. Now, fellas, I want you. Thanks a lot. I really appreciate it. Okay. Stand right here. Okay. And what's your first name?
Jake.
Jake. And what's your name?
Javier.
Javier. Okay. Javier and Jake, I want you to mount up on your skateboards, and I want you to face each other. Okay. All right. And I want you to face each other, and so that you can touch like this. Okay. So like patty cake. All right. Now get up on your boards. All right. Now what we're going to do is I'm going to count to 3, and I'm going to say the word go. And Jake and Javier, when I say go, I want you to push off as mightily as you can. Ready? 1, 2, 3, go! Yay. Now, Jake, you pushed off. I mean, you bench pressed Javier off. Okay, and Javier, you bench pressed Jake off that way. But notice that Javier went off to the right. Jake went off to, wait a minute. Javier went off to the left, your left, and Jake went off to the right. All right, let's try to switch sides. Let's see if this is reversible. You know, because like if you're in a science fiction movie, you know, there's some scary monster sneaking up on you, and you can't destroy it any other way. A lot of times they'll say, reverse the polarity, and that kills the monster. Okay, so we're going to reverse the polarity here. See if this still works. Okay. Ready? 1, 2, 3, go! Yay. All right. So when Javier pushes to the left, he goes flying to the right. When Jake pushes to the right, he goes flying to the left. Now I want you guys to come over here to the corner. Okay. Now, I want you to, Javier, you're going to go first. I want you to mount up, back. I want you to push it off the middle. 1, 3. 1. Get a little closer. 1, 2, 3. Yes. Now, Jake was just sitting here, but somehow Javier got a push to the right, or to the left, off in that direction. Okay, let's try Jake. Yay. Same thing. Now, what does that tell you about the wall? What is the wall doing? It's pushing, just like Javier pushed Jake and Jake pushed Javier.
It's force.
It is. The wall is exerting a force, even though you can't really see. You know, you can't see the wall's not doing this. But as you'll read about in the textbook, the surface of this wall is rigid. Okay? And the network of molecules and atoms kind of forms like a trampoline. And when you push on it, it pushes back, just the way a trampoline does. You know, when you get on a trampoline, the trampoline sinks down, and the springs expand a little bit until they support you. Then you stop sinking down. And when you jump around a little bit, it'll push you up into the sky, and you start doing flips and all that stuff. Right? Same thing here. This will, like you can't put like an elephant on a trampoline; it'll smash into smithereens, right? Same thing here. If you were Iron Man, you couldn't, push into this wall, and the wall, there's at some point where the wall is going to break down. But for these two guys, they're not Iron Man. They're not wearing Iron Man suits, and so they can't demolish the wall. So that means there's some rigidity force in this material. Second note, are you taking notes? Should be. Second note. Sir Isaac Newton. It's pathetic, yeah. Second note. You can't make a wall in a house with water. It doesn't have any rigidity force. Matter of fact, the only rigidity force that the water surface will have is just a little bit, it'll support a leaf or a mosquito or something like that, but not like a skateboarder or even a skateboard itself. It'll sink into the swimming pool or the bottom of the bucket. Right? But something small, yeah. But normally water, not much rigidity force. But something like this. It's not, can't make a good enough noise in there. I'll figure out some way. Anyways, so the rigidity force in the material, thanks, fellas. And let's give them a hand. The rigidity force in the wall is provided by those molecules, and you will read about that in chapter 3. So let's jot down a few things in your notes. And I'm going to insert this, a PDF image of the notes that we're going to do on the document camp. And unfortunately, the first hour podcast got all screwed up, so they're going to have to use this as well. That's all right. All right, so, I don't need the earphones. All right, so PSC 1121 01 3117. Okay, notes on skateboard demonstration. Okay, Javier and Jake. Okay, now I'm going to draw kind of a hokey picture. A couple guys on skateboards. I'm not like the best stick figure artist, but okay, here's these two guys, Javier and Jake, pushing off from each other. Okay, so they just pushed off. Now, a couple things I want to go through with you. Sir Isaac Newton's third law of motion says that the amount of push force that Javier puts on Jake is equal to the same size as the push force that Jake puts on Javier, with one modification. They're opposite directions. Okay? So the way that I'm going to write that is by writing, this is what we call chalkboard boldface to represent a vector. We got two guys that are both letter J for the first. Jake, what's Jake? Your first letter of your last name. P? P for Papa. Javier, last name. Okay. So, force of Jake on Javier. Okay, now this is chalkboard boldface. It kind of looks like it's an outlined letter. That means it's a vector. Okay, and that's equal to the opposite of the force of Javier. Wait a minute. Cross this out. I'm going to cross that out. I'm going to draw an arrow first. I'm going to draw an arrow right about here, the middle of Jake. And the same size arrow to the right. Okay, this looks better. And I'm going to label it up here. F from Jake on Javier. That arrow represents the force vector from Jake on Javier. Okay. And this one over here, this arrow, represents the force from Javier on Jake, P. All right? Now I can write down Newton's third law. Newton's third law says that the force from Javier on Jake is equal but opposite in size to the force from Jake on Javier. All right? So, equal in size. Opposite direction. Now, the colloquial way of saying that is for every action there's an equal but opposite reaction. But really it's a statement about forces. Question? Yeah, this minus sign here means whatever this says that the force of Javier on Jake is the opposite direction of the force of Jake on Javier. All right, so that's what that minus sign means. Now, here's another way that you could write it using numbers. Okay, this is a leftward vector here. So let's say that the size of this force is 100 newtons. That means I would write negative 100 newtons over here and positive 100 newtons over here for those two guys. All right? So that's another way to look at the negative signs. And look at that. The force of Javier on Jake is the opposite of 100. All right. The opposite of 100 is negative 100. All right, so that's good. All right, now, a couple other notes here. Let me ask you a question about the contact time, delta t. So these guys, they're in contact, but they're not exerting force on each other until I say go. All right? So here's an kind of a mental IQ test question. Which individual is in contact the longest? Jake, because he's taller, or Javier, because he's shorter? Which one's in contact the longest? What do you think? It doesn't matter?
I mean, like in contact with them touching,
Yeah.
their height doesn't matter.
The height doesn't matter because it's contact. But, all right, so what if they were the same height? One of them would have a longer contact time, wouldn't he? You know, so you're saying no? Well, what if one guy had more mass, was same height but had more kilograms of mass? Wouldn't that mean they would have a longer
But what does that have to do with them touching?
All right. Good. So contact time. Think about it. If Javier is in contact with Jake for 0.1 second, then Jake's in contact with Javier for 0.1 second. All right? So the contact time is the same. All right? But F equals ma is going to look a little bit different. Now, that's Newton's second law. Let's put it together. All right? The force of Javier on, and I'll write this as a vector statement, on Jake. Okay, now this is on Jake. So this is going to be equal to the mass of Jake, m subscript p, times the acceleration vector. Now, here's a boldface, chalkboard boldface for the acceleration on Jake, a subscript p. Right now, the force from Jake on Javier is equal to, okay, now this is on Javier, so this is the mass of Javier times the acceleration on Javier. All right? Now, acceleration, that's delta V over delta T. So this is the same as m subscript p times delta V vector for Jake divided by delta T. And that contact time is that's the amount of time that they're accelerating. You know, so once they break contact, they're no longer accelerating. Well, the floor is going to, accelerate them to a stop by friction, but they're not accelerating each other after they break contact. So now over here for Javier, mass of Javier times delta V for Javier over delta T. All right? Now, the size is equal to, the sizes of these are the same. All right? The directions are opposite. The direction of delta V here for Jake, if Jake moves off to the left, then the delta V for Javier is going to be off to the right, and vice versa. So these are vector let me make this boldface. Okay, chalkboard boldface for delta V subscript A. All right. Now, I'm going to, can you get me my red pen? I'm going to use red ink. Oh, I'll use yours. Okay. I had one in the pouch. All right. Now I'm going to circle the two things in each equation that are the same size. All right. Delta T, that's the same size on each. The forces are the same size, although they're different directions. All right. Now what that means is that I can form a new equation, and that new equation involves the concept of impulse. And if you read the first section of chapter 4 for your homework tonight, you will have, you'll be ready to start tackling the idea of impulse, and it comes from Newton's second law and the idea of interaction. Question? Oh, sorry. Okay, yeah, here's your concept. Impulse. I-M-P-U-L-S-E. Sorry about that. Okay, can you go back to the laptop now? All right, now I want to talk about some examples of forces in two dimensions with you. And you're going to have some homework tonight in homework 5 that involves handling two forces that combine for a net force, and the two forces are going to be in different directions. Right? So we want to be able to handle, something that's not left and right, something that's not up and down, something that's maybe a combination of those. Okay, so we're going to use Pythagorean theorem, and then we're going to use basic directions. So we're not going to use all the trig formulas to get the size of the tilt angle and stuff like that. If you've had trig class, which some of you have had, you know how to do that. But what we're going to do is just use basic directions, 8 of them. Okay, the first 4 are north and south, east and west. Okay, right? And then the other 4 that we're going to use are here, northeast, southeast, southwest, and northwest. All right? And so when we work in 2 dimensions, we're not going to get too fancy with directions. All right? You know, down to the nearest degree or anything like that. We're just going to round off to northeast, east, southeast, south, southwest, west, northwest, or north. And actually, the 4 cardinal directions, north, east, south, and west, those won't be rounded off. But everything else other than those will be rounding off to northeast, southeast, southwest, and northwest. Now, I want to work at it, another example with you on the document camera. And I'll embed this in the YouTube. Let's leave this over here. So this is 131:17, page 2. And let's do a pair of forces, F1, 100 newtons to the east, and F2, 60 newtons to the north. Okay? All right, and these are what I call the constituent forces that constitute the net force. So we're going to get the net force. And the way to do that is to draw a dot to represent the center of mass of your object. And then, let's see, a vector, here's F1, a good big arrow to the right. And then this one's going to be smaller. Okay, so these 2 forces are acting on my object here at the dot. Okay, so instead of drawing a car or a baseball or something, I'm just drawing a dot for simplicity. All right, now this thing's getting some rightward, it's getting some eastward and it's some northward. So its direction is going to be northeast. Let's figure out exactly what it looks like. The way to do that is to use these 2 vectors to form a rectangle or a parallelogram. So kind of trace in your rectangle. All right. And this is 60, and this is 100. This is 100. This is 60. And then the net force is simply the diagonal of that rectangle. Okay, so here's your F net for this example. All right. And let me draw a copy of that. And note here, I've labeled the hypotenuse F net, but I've no longer indicated that it's a vector. When I don't make it boldface F net, that simply means the magnitude. That's how many newtons I've got on that hypotenuse. We're going to figure it out using Pythagorean theorem. 10 squared plus 60 squared. There's what? Oh, sorry, thank you. Dude, forgot a 0. That's pretty significant. Okay, 10 squared plus 60 squared equals F net quantity squared. Right now, you can, and actually we already know the direction. It's northeast. You can see it from this picture. And now we're going to figure out the size of it. Okay, so 100 squared is 10,000. And 60 squared is 3,600. And that's F net squared. So let's see, that's 13,600 is equal to F net quantity squared. So now you have to square root that. So the square root of 13, get your calculators out. Don't let me catch you napping. The square root of that is F net itself. All right, so that works out to what? Like 130? What? 116? Okay. 116? All right, give me two, let's see, 116 point what? Give me one digit. 6 newtons. Now, students, all up in here, I didn't write my newtons in. Okay, but I made sure to write it in down here at the very end. Okay, so don't forget this. All right, so now I can write down my final result. F net equals 116.6 newtons, comma, northeast. All right. And so you'll have a little bit of thinking to do with stuff like that tonight in homework 5. Questions before we go to the next example? Go ahead. Constituent forces. These two are constituent forces. They constitute the net force. In other words, they go into the net force. The fancy equation is this. F net, this is a vector equation. F1 plus F2. All right, you add up all the forces. But I mean, this is a kind of an equation. This is how you do it graphically over here. All right, right in here. Another question before we continue? Yes.
On the homework, are we gonna be able to like do a little bit and then come back, or is there a time that like do we have to do it in one sitting?
That's your answer. No.
No.
Yeah. Didn't you hear that? My phone went ding. Yeah. No. No, you got to do it all at once. But you're going to have 4 tries. So.
Okay.
Right. But it's. I think I've set it for 60 minutes though. I don't know. Can you look and see what the time limit is? But you'll have 4 tries. It's mostly multiple choice, but there's a few calculations. So it's. All right. Let's keep going. Let's do another example. Oh 01, 17, no, 01, 31, 17, page 3. Okay. All right, 2 more constituent forces. Here they are. F1 equals 17 newtons north, and F2 equals 8 newtons west. All right. So let's draw a dot. And my big vector is north. So that's F1. And my other one is west, so it's a little bit smaller. And if your picture is about like this, that's good. It's, if you're not another Rembrandt or Michelangelo, for diagrams, that's all right, because we're going to let the numbers do the talking. All right, now we can draw in the rectangle or parallelogram. If they're slanted, if they're not at right angles, you'll have a parallelogram. But if they're at right angles like this, you just have a rectangle. Here's your diagonal. Whoa. That's, I better do that again. See if I can get this nice and straight. There we go. Ooh, that's better. All right. So there's my F net. So before I do anything else, graphically I can see, okay, northwest is going to be my direction. Let's figure out the magnitude. All right. Pythagorean theorem, F net squared equals, let's see, 17 squared plus 8 squared. Let me draw a backup You can draw your triangle like this, just the same. That triangle does the job. Anyways, let's see, 17 squared is 289. 8 squared is 64. 64 minus 11 is 53. So double check me, this is 353, correct? Okay, 353. So F net itself is the square root of that. Okay, and so F net magnitude is, I don't know, what is that? 18 point what? 18.8? 18.8 newtons. All right, so your final answer, vector-wise, F net is 18.8 newtons, comma, northwest. Whoops, gotta spell northwest right. All right, now, if you know your trig ratios and stuff like that, you can figure out the exact degree of tilt. But for us, northwest is going to be sufficient. Okay? King.
Will we ever get like direction like northwest and north at the same time, or no?
Kane just asked the question, will we ever get two constituent forces, one of which is slanted, like northwest, over here, and the other one straight like a north? And the answer is not here, but in the textbook, yes. All right, so there's an example in the textbook, and so follow that one, and that'll be example 3. Okay. Questions before we continue? Display, please. Thank you. All right. Now, in this slide here, in the podcast, in the YouTube, I'm going to insert this last example. So all these things will be in the YouTube in one way or another. Okay. Now, just so you know what our plan is for homework, I want you to finish reading chapter 3. So, and then read ahead into chapter 4, section 1. That'll go into the idea of impulse. You're not dismissed yet. I want to talk to you about the exam for just a minute. Tonight you also have a regular homework. It's ginormous, number 5. It'll activate in about 7 minutes. Finally, your first midterm is next Tuesday. Thursday night, you're going to have a big homework assignment. Part of it will be review. Part of it will be about Thursday's concepts. And then I'm also going to put in the 2 brain burners again from homework 4 so that you can give them one more shot. See if you can practice. And I'll make sure to give you plenty of time to get these homeworks done. All right. Now you're dismissed. 1:14. A little bit early today. Thank you.
Also, the homework is 45 minutes.
Is it?